The AP Chemistry exam is just days away, and I know you're all working hard to make sure you get every single point you deserve on that exam. Hi there, my name is Jeremy Krug, and we're going to have a little cram session. We'll be working our way through all 9 units of the course over the next hour and a half or so. And if you need some more practice, don't forget to check out my detailed videos right here on YouTube that cover all 91 topics in the course, as well as full study guides, practice exams, and more over at ultimatereviewpacket.com. Now, let's get started.
So just so you know, we're going to go through this entire course from the beginning all the way through to the end, and we're going to hit as many high points as we can in this cram session. So as you follow along, try to work the problems with me, and I think that's going to help you quite a bit as we get ready for the AP exam here in just a few days. So the first item I'd like to share with you is mass spectrometry. So often what you'll have in a question like this is you'll see a graph that looks a whole lot like this, to be honest. Each bar represents an isotope, and on the x-axis we have the atomic mass of the isotope. So for example, this graph represents 2 isotopes because we have 2 bars there. One of the isotopes has a mass of 85 atomic mass units. The other bar, the other isotope, is representing a mass of 87 atomic mass units. The height represents the percentage abundance of each of those isotopes. So this first one here, that's the tall one, it looks like that's somewhere around, probably around 75% abundant of all the atoms of that isotope. This other short one seems to be somewhere around 25%. You can take the atomic mass of the isotope, which is 85, multiply it by the decimal equivalent of its percentage, which is 0.75 here, and you get 63.75. Do the same thing for the other isotope, so the 87 times the 0.25, which is 25%, and you have that product. Then you add those two together, and you find that the overall average atomic mass is somewhere around 85.50. Now, this is an estimate because it's kind of hard to tell exactly how tall these are, but this is a really good estimate. Now, we can match this up to the periodic table, and we can see what element we're talking about. So this seems to be rubidium because it's very, very close to that atomic mass that we had estimated. Now, very often, you'll see these types of questions pop up in the multiple choice section of the test. And so you might have a question like this where there seem to be 5 different heights of bars here. That represents 5 isotopes. And so what we have to do is determine which element we have. And so it's not so important necessarily that we calculate an answer if it's a multiple choice question, but we can estimate the mass. And we can probably just eyeball that. You can see that this mass over here with about 64 is, about half of the atoms, and we have several that are in the 67, 68 range, a few that are higher or lower. But we could kind of eyeball this and say that the overall weighted average here is probably somewhere around 65, somewhere in that neighborhood. So what we could do is we could match this up to the periodic table and find an element that has the closest atomic mass to about 65. And we find that that would be zinc. And so if they give you 4 choices, one is zinc and one is hydrogen and one is uranium or something like that, it should be pretty obvious as to which element you're talking about. So that's mass spectrometry. Now, another important point that pops up in Unit 1 is periodic trends. And so there are these trends or these patterns on the periodic table that you need to be very aware of as you work through the exam. So the first one that I want to share with you is atomic radius. Now, generally speaking, atomic radius is the greatest at the left and the bottom of the periodic table. So that means these elements down here, like cesium and rubidium and all these over here, those are going to be the largest elements on the periodic table. And the reason that's the case is that atoms at the bottom of the periodic table have more electron shells. They have more occupied energy levels. And because of that, that last shell is the farthest away from the nucleus. And so it's important that you're aware of that so that if this is on an essay, you're able to explain that. Now, atoms toward the left side of the periodic table have a less effective nuclear charge. Now, what that means is, all of these atoms in period 6, for example, all have 6 electron shells. And so you might think that their atomic radius is about the same. The thing is, the atoms on the left side have fewer protons to pull in those 6 energy levels, or those 6 electron shells. So that means that those outermost electrons can veer farther away from the nucleus, and so that's why these atoms on the left side are larger and the ones on the right side of the table are smaller. Now, another trend that you want to be aware of is ionic radius. And here is a nice graphical representation of that. As you can see, just generally speaking, cations, the positive ions, tend to be smaller than the negative ions, the anions. And if we look at just a few of these here, let's look at the nitride, oxide, fluoride ions, as well as the sodium, magnesium, and aluminum ions. You'll notice that if you start looking at the number of protons and electrons and those electron configurations there, they all have the same number of electrons. So in chemistry, we say that they're isoelectronic. They all have 10 electrons. So why do they all have very different sizes? In fact, aluminum is absolutely tiny as far as an ion goes compared to nitride. Well, the reason is the atom with the most protons, if they're isoelectronic, is going to be the smallest. And that's because it has more protons, right? Aluminum has, something like 13 protons, I think. So it can pull in those electrons a whole lot more tightly than something like nitrogen, which only has, about 7 protons, I believe. So, we see that the one that has fewer protons is going to be the largest for isoelectronic species. Now here's another trend that you want to be aware of. First, ionization energy. And generally speaking, this is going to be greatest toward the right and the top of the periodic table. So these elements like helium and neon and fluorine up here, they're going to have very high first ionization energies, and the ones down here toward the bottom left, like cesium, they're going to be very, very low. And the reason for that is that atoms at the top of the periodic table have fewer electron shells. So that means that that last shell is a whole lot closer to the nucleus. And so it has stronger attractions to its outermost electrons. We say it has stronger Coulombic attractions to its electrons. Now, on the right side, it's kind of the same way as we had for atomic radius. On the right side, you have greater effective nuclear charge. So that means that since you have more protons as you go to the right, it's going to be able to pull in those electron shells a whole lot more tightly than those atoms that have fewer protons. And so that's the reasoning that you want to share with your reader if you have an essay question about this. Now, if we look at another concept, this is something called photoelectron spectroscopy, and this will appear on the exam. You're going to have a photoelectron spectroscopy graph here, and what you want to realize is that each one of these peaks represents a sublevel. And so it's important that you're able to write electron configurations. The way this works is it goes from left to right in order of increasing energy. So that means you have 1s is always the first one, and then 2s is your next peak, and then after 2s is 2p. After 2p is 3s, and after 3s is 3p. So those are the sublevels that are represented in this PES diagram. Now, the height of each peak represents the relative number of electrons that you have there. So notice that the 1s, the 2s, and the 3s peaks all have the same height. And if you've been studying chemistry for very long, you know that those sublevels max out at 2 electrons, don't they? So these all are 2, 2, and 2. Now notice that the 2p peak here is exactly 3 times taller than those s peaks. So that means it has 3 times as many electrons. 2 times 3 is 6, so this is 2p 6 right here. Now this 3p electron, it seems to be, I suppose you could say 5/6 as high as the 2p peak, so that means that this peak has 5 electrons in it, so that's 3p5. And so if you know your electron configurations, you can, look at the electron configuration that this graph represents and determine that we're talking about the chlorine atom here with this particular PES diagram. Now, let's try another one. Let's say we have this PES diagram. Hopefully, you can plot out those sublevels just like I did before. It goes 1s, 2s, and 2p. And then we know that the s's have 2 apiece, so it's 1s2 and 2s2. And the last peak is about, 1.5 times as tall as the s peak, so this represents 3 electrons, so it's 2p3. And if you look at the periodic table, you can see that we're talking about nitrogen here, something that has 7 electrons. And so that's how you can interpret a PES diagram. There are some more involved things here, as there are with lots of the topics that we're going to hit in this cram session. And of course, you can check out my full-length videos. Of course, here before the exam, we just kind of want to hit the high points so that we get those things back in our memory. Now, let's take a look at Unit 2. And one of the very important parts of Unit 2 is being able to draw a Lewis electron dot diagram. So if you have a molecule like sulfur difluoride, you need to realize that the central atom, of course, goes in the center of your structure. So I'm going to put sulfur in the middle here, and we have the 2 fluorine atoms, one on either side. I always recommend to students that you start with the outside and you work your way toward the center. So we have fluorine, and fluorine, if you look at the periodic table, group 17, it has 7 valence electrons. So I'm going to put 7 dots around this one and 7 dots around that one right there. And sulfur is in group 16, so it has 6 valence electrons. So I'm going to put 6 dots around the sulfur there, trying to pair these up as much as I can, and we have that. So now, the goal is, we're trying to follow the octet rule if at all possible. Does everything have 8 valence electrons? And yes, indeed, everything does. We have the fluorine can lay claim to these here in the middle. We have a couple shared pairs here. Everything has 8. So this is a good structure. So you can write your Lewis electron dot diagram like this. A lot of students like to replace the shared pairs with a line, so you can have something like this, and that's good as well. So there's the Lewis electron dot diagram for sulfur difluoride. Let's try this next one, which is COCl, which is a chemical compound that has carbon as its central atom. So once again, just like in the last example, we're going to always start with the atoms on the outside and work our way toward the inside. So this chlorine down here is in group 17, so 7 valence electrons, so I'll put those there. And then the same thing with the chlorine atom on the right, 7 valence electrons right there. And then the oxygen is in group 16, so it has 6, so 6 dots for that. And the carbon is in group 14, so 4 dots, 1, 2, 3, 4, trying to pair these up as I can. And now I am trying to get everything with 8. So does everything have 8 valence electrons the way it's drawn in this structure? Well, no, it doesn't, does it? The oxygens and the chlorines there all have 8, but the carbon only has 6, the way it's drawn here. So what I have to do is move some electrons from the outside to the inside. So I think I'll take these 2 dots on top of oxygen and move those down like that, and now everything has 8. And so what I have here is 2 single bonds with the carbon and chlorines there, but I have a double bond between carbon and oxygen. So when I draw the structure, it's going to look like this. So we have a good example with a double bond there. Now let's take a look at type of bonds and hybridization. Now we know that this structure here has 2 single bonds. Now just so you know, every bond that's a single bond is a sigma bond. So that means this molecule has 2 sigma bonds. And the way you find the hybridization is you take the number of sigma bonds touching that central atom and you add the number of unshared electron pairs on that central atom as well. So in this case, we have 2 sigma bonds plus 2 unshared electron pairs. 2 plus 2 is 4. That's called the steric number, and that corresponds to a hybridization of sp3. Now you have to know that. They're not going to tell you that on the exam. So in this case here, we have 2 single bonds, but there's a double bond here. Well, a double bond is composed of a sigma and a pi bond. Pi bonds don't count toward hybridization or molecular geometry. So this molecule has 3 sigma bonds plus 0 unshared pairs. That's a steric number of 3. And so that's going to be a hybridization of sp2 because it has 3 sigma bonds, 1 pi bond, no unshared pairs on that central atom. Now, we can also do this for somewhat more complex molecules that have multiple central atoms. So this organic molecule here has 3 carbon atoms that are all essentially functioning as a central atom. So carbon number 1 has a single bond and a triple bond touching it. Well, don't forget, a triple bond has 1 sigma and 2 pi bonds. So if we want to add up the total number of bonds here, we have 1, 2, 3, 4, 5, 6 sigma bonds. And because there's a triple bond there, that's 2 pi bonds. So that's why it's 6 sigma and 2 pi bonds. Each central atom, each carbon atom here, has its own hybridization. So carbon number 1 has 2 sigma bonds touching it, no unshared pairs. So that steric number of 2 corresponds to sp. And carbon atom number 2 is the same way. It's got 2 sigma bonds, no unshared pairs. So that's sp hybridization as well. And then on carbon atom number 3, we have 4 sigma bonds, no unshared pairs. So that's sp3 hybridization because its steric number is 4. Now, we can take this a step further and talk about the molecular geometry and the bond angle for each of these molecules. So on this one, we have a molecular geometry, since it has 2 sigma bonds, 2 unshared pairs, that's called a bent geometry. Now, you might be thinking that doesn't look bent. It has a bond angle of 105 degrees. It doesn't look like that the way it's drawn. As it turns out, most chemists will not draw a bent molecule like this. We actually draw it more like this to kind of reflect the bent structure that we actually have in the real world. So just be aware of that whenever we draw these. On this next molecule, the COCl2, we have 3 sigma bonds and 0 unshared pairs. Well, that's called trigonal planar, and that has a bond angle of 120 degrees. So you have to know that. Now on this last molecule here, since there are 3 central atoms, guess what? There are 3 molecular geometries. The first one is linear because it's 2 sigma bonds, no unshared pairs. The same thing for carbon number 2, it's linear as well. For carbon number 3, we have 4 sigma bonds and no unshared pairs. That's called tetrahedral. Now you need to know that linear is 180 degrees, tetrahedral is 109.5 degrees. So there isn't a whole lot of memorization on the AP exam, but those molecular geometries and bond angles and hybridizations, those are things that you do need to remember for the exam. Now, another property that we can talk about in terms of these molecules is it polar or is it nonpolar? Now, if a molecule is a polar molecule, that means that it has a lopsided electron distribution. It's almost like it has an unbalanced region of negative charge on the molecule. It doesn't really have anything to do with is the molecule symmetrical or not. That is a common misconception. Doesn't have anything to do with symmetry. For example, this molecule here, SF2, it's symmetrical, isn't it? But it's a polar molecule because there's this lopsided electron distribution. Up here at the top, we have these 2 unshared electron pairs, and that makes it a polar molecule. Now, what kind of intermolecular forces does this have as we kind of ease our way into Unit 3? Well, we know that every molecule, no matter what it is going to have London dispersion forces. So if you see a question and it asks what kind of intermolecular forces does it have, you'll never go wrong by saying London dispersion forces. However, polar molecules also have dipole-dipole forces. So this one here has both dipole-dipole and London dispersion. Now this second one here, this is also a little bit lopsided, isn't it? We have, 4 dots, those 2 unshared pairs, whereas these have 3 pairs. That's a polar molecule as well. And so that means we have London dispersion forces, and we also have dipole-dipole forces. Now in this last structure, notice that there is no lopsided electron distribution. Everything seems to be very even. There are no unshared electron pairs that aren't canceled out by something else. So this is a nonpolar structure. And considering that it's nonpolar, it would only have London dispersion forces. So that's one of the ways that you can figure out the intermolecular forces. You really need to draw the structure and see if it's polar or nonpolar to see what kind of forces it's going to have. Now let's take a look at this molecule here. We have the ammonia molecule, NH3, and hopefully you can see that it's a very polar molecule. We have this unshared electron pair that's just hanging out up there, not canceled out by anything else. So it's absolutely a polar molecule. And so it's going to have intermolecular forces that are London dispersion. It also has dipole-dipole, but this is a very special type of dipole-dipole force. If you have a molecule that has a nitrogen-hydrogen bond, or an oxygen-hydrogen bond, or a fluorine-hydrogen bond, it's also going to have this hydrogen bond. So instead of calling it dipole-dipole, we just go ahead and normally call it hydrogen bonding. So that's how you'd discuss the intermolecular forces for that molecule. Now, what about something that's a little bit different here? This is not really a molecule, is it? Sodium fluoride is not really a molecule at all. It's an ionic compound. So the forces that it's going to have in between its own structure would be ionic forces. And as we think about ionic compounds, these are structured differently than molecular or covalent compounds. They have this lattice structure. Now, of course, this would be a three-dimensional structure in the real world. I'm just simplifying it to make it look like this on the screen here. But you can see how every sodium and every fluoride, these are kind of alternating each other. And so that's the structure of an ionic bond. These ionic compounds don't exist in individual molecules like ammonia or the phosgene molecule would. They are in this nice repeating lattice here. Now, as we talk about ionic compounds, there's another force going on here that you need to know about. These are called ion dipole forces. And the College Board kind of calls this an intermolecular force. It's not exactly an intermolecular force, but it is. This is a very important force that you need to know about. And it is the force between individual ions in a compound and polar molecules, like water is probably the best example. If you take sodium fluoride and dissolve it into water, well, we know that water molecules are very polar. They have a negative pole and they have a positive pole. And in the case of water, the side that has the hydrogens here, that's going to be the positive pole of water. And the oxygen side over here, that's the negative pole. So what happens is these water molecules are going to surround that fluoride ion right there, and they're literally going to drag that fluoride ion away. And this is what an ion dipole force is. It's the force between the individual ions and the polar molecules, the individual poles in the polar molecule. And that's essentially how ionic compounds dissolve in water. If a substance is soluble, if it's ionic and it's soluble, that means that this ion dipole force is essentially stronger than the ionic forces holding this thing together. We could say the same thing for the sodium over here. If we had water molecules surrounding that sodium over there, the negative pole of the water molecules are going to be attracting the positive sodium ion. So that fairly strong ion dipole force is literally going to drag that sodium ion out of the structure. And so that's how these ionic compounds dissolve in water. You have these ion dipole forces that are actually taking place here. Very important force to know about. As we move on, let's take a look at some gas laws here. So this is also part of Unit 3, knowing about the gas laws. So here we have a gas mixture that is collected in a 2.00 liter rigid container at a temperature of 295 kelvins. If the pressure inside the container is measured to be 1.02 atmospheres, how many moles of gas are in the mixture? So we have a perfect setup here for ideal gas law. We have a pressure in atmospheres, we have a volume, we have a temperature, we want to know the moles. So we just have to plug and chug into this equation here. So the pressure is 1.02 atmospheres, we just plug that in, and the volume is 2 liters right there. We're trying to find moles, so N is going to be our unknown here. R is that universal gas constant. It's 0.0821 liter atmospheres per mole Kelvin. On the exam, they actually give this to you with one extra significant figure, 0.08206, so I'm going to go ahead and use that number here. Temperature is 295 kelvins. So we just do a little bit of algebra here, and we can find that the number of moles of gas in the mixture is about 0.0843 moles. And so that's how we would solve a fairly straightforward ideal gas law problem. Now, what if we have this? What if it is determined that 0.0329 moles of that mixture is oxygen? The other gas would compose how many moles? Well, if you have two gases and they have an individual amount of moles, they're going to add up to give you the total moles, aren't they? So if the total mole value is 0.0843 and one of the gas is 0.0329, we just have to subtract. And so the other gas is going to be 0.0514 moles. And so that's how we'd solve something like that. Very simple, just subtraction here. Now, let's go a step further. If it is determined that this other gas has a mass of 0.2056 grams, what is the molar mass of this gas? Well, all we have to do there is recognize that molar mass is measured in grams per mole. And so that implies we have to take grams and divide it by the moles. Well, the problem tells us that it has 0.2056 grams. And the number of moles, well, we just got that from the last problem. It was 0.0514 moles. So when you divide that out, it's about 4.00 grams per mole. So if I had to guess by looking at the periodic table, I'd say that we're talking about helium in that other gas there. So let's take a look at another important concept that is going to show up on the exam. And this is spectrophotometry. And this is where we take an instrument called a spectrophotometer, and we're trying to use it to measure the concentration of a certain ion or compound or something like that. Now, normally the way this is presented on the AP exam is we have a graph. And the graph is going to look something like this, where we have on the x-axis the concentration of the substance, whether it be the ion or a molecule or something like that, is presented on the x-axis, and the absorbance that is read right off of the spectrophotometer is plotted on the y-axis, on the vertical axis here. So the first thing you want to do when you're doing an experiment like this is to run a blank. And so I'm just going to do a quick check and make sure that there's a blank. So we'll have a little dot there at the origin, 0, 0, to show that we have a blank. That when there's no ion that we're looking for in here, that the absorbance reads 0. That's what you want to start with. Then we're going to run several known concentrations and we're going to record their absorbances. And so as we do that, we just plot those on the graph like this. We have a bunch of dots. Now notice that these dots roughly give us a line. So we're going to draw a best fit line. It's not going to be perfect, but we should have a pretty good idea as we draw that best fit line. So it's probably going to look something like this as you draw that. Now this is sometimes called a calibration curve. I know it's a line, but we often call it a calibration curve in chemistry. And now we can determine the absorbance of our unknown and match it up to its concentration. So if we run the unknown, maybe it has an absorbance of right here about 0.20. So we just line that up to the best fit line, right like this, and we drop down and we can see that the concentration of the unknown seems to be right around 0.55 moles per liter. So that would be our concentration of the unknown. Very simple, basically just being able to read a graph as you do that. Now, a couple of things that sometimes they do throw at you, especially on the multiple choice section. Watch out for outliers. And so they like to ask these questions. If you have a calibration curve like this and you see a random dot that's kind of off the line, it's like above where it ought to be, that's probably because the sample got contaminated with some solution that had a higher concentration than you expected. So maybe, according to this, maybe you had, you had a 0.25 and it's way up here. Maybe it got contaminated with some 0.60 molar or something like that. Or if you have an outlier that's like way down here, it's way down below the line, that's probably a sign of a sample that got contaminated with distilled water, most likely, as you were washing out the cuvette, or possibly it was contaminated with something that had a concentration that was too low. So maybe you thought it was 0.35, and it actually got contaminated with something that was like a 0.1 or something like that. So just be aware of those outliers. They like to ask those questions on multiple choice, so we have that. Now, going on to Unit 4, we're moving right on to the concept of net ionic equations. And so when we write equations, especially if it's in solution, you need to understand that there are ions in solution. So if we have this reaction here where a piece of magnesium metal is added to a solution of zinc chloride, the first thing that I like to do is write out what you have on the reactant side. So the magnesium metal, of course, is just Mg. So we write that. And then the solution of zinc chloride, well, anytime you have a solution of an ionic compound, it's existing in its ion form if it's soluble. So zinc chloride will exist as zinc 2 plus ions and chloride ions, Cl negative. Now, we have to remember that generally speaking, if we have ions and metals kind of mixed together, metals are going to react with metal ions. And likewise, if you ever have a nonmetal, the nonmetal is going to react with nonmetal ions. Well, in this problem, we have a metal, which is the Mg, and we have a metal ion, which is the Zn2+. So those are going to react with each other. Now, what's that chloride going to do? Well, the answer is not going to do anything. It is a spectator ion. Do not include spectator ions in your net ionic equation. That's a very common mistake that students make on the AP exam. Do not include those in your net ionic equation. So the way this works is the magnesium is going to have to turn into something else. Well, the only other form of magnesium I can think of is Mg2+, right? That's the ion form of magnesium. And then the zinc 2+ is going to have to turn into zinc metal. So we'll have the Zn. And so now we get to balance these. On the first one here, it looks like I can balance this half reaction by putting 2 electrons on the right side right here, balancing out the charge. And then on the second one, I can balance the charge by adding 2 electrons to the left side, just like this. And just so you know, whenever we have a case like this where we're losing electrons, that half reaction is called oxidation. Or if you prefer, the charge on the magnesium is going up. That's also oxidation, going from a 0 to a +2. That means that the second one is a reduction because we're gaining electrons and the charge on the zinc is going down from +2 down to a 0. So now we can add these together and we have our overall balanced equation. This is an oxidation reduction process. We often call that redox. Now let's try another one. What about sodium metal is burned in air? Well, sodium metal, of course, is Na. And when something is burned in air, it's always being reacted with oxygen gas, O2. So essentially, we just have to put those two elements together to make sodium oxide, which is Na2O. And we have to balance these equations. Probably want to balance the oxygens by putting a 2 right here. And then I have 4 sodiums on the right side, so I put a 4 over here. And now I have a balanced equation. On the next one here, we have a sample of propane gas, C3H8, that's burned in air. So kind of the same thing, except this time we have C3H8 being reacted with O2. But anytime we have a complete combustion reaction, we know that the products are going to be carbon dioxide and water. And so we can write those out. We need to balance this. I can balance my carbons by putting, let's see, 3 carbons over here, so a 3 right here. I can balance my hydrogens. I have 8 hydrogens on the left side and only 2 on the right side. So if I put a 4 right there, that balances the hydrogens. And then the oxygens, well, I have 6 plus 4 more oxygens right there, which is 10. So by placing a 5 in front of this oxygen, now I have a balanced equation. So we have that. Now let's try a precipitation reaction. Let's say we have solutions of lead 2 nitrate and sodium carbonate that are mixed in a test tube. Once again, realize that if you have an ionic compound and it's soluble, it's going to be in its ionic form. So lead 2 nitrate solution is actually Pb2 plus and NO3 with a negative charge. We have those ions kind of swimming around. Then we have sodium carbonate, same thing, we have sodium ions, and then we have carbonate ions. And our job is to determine which of those two combinations is going to make the solid precipitate. Now, in college chemistry or in general chemistry, you actually do have to learn all those solubility rules. On the AP exam, they give you kind of a gimmick where they tell you that anything that has a group 1 ion in it, or a nitrate, or an ammonium ion is going to be soluble. And the other substance is going to be your precipitate. So that's kind of how they write these questions. That way you don't have to learn all of those solubility rules for this course. So we notice that sodium and nitrate are in one of the combinations, and so those are going to end up being our spectator ions. So that means that the lead-2 ions and the carbonate ions are going to get together to make the lead-2 carbonate. So that's what we would have as our product, which means that the sodium and the nitrate are spectator ions. So if I clean this up, I can write the net ionic equation like this. Lead-2 plus aqueous plus carbonate aqueous makes our PbCO3 solid precipitate. So that's how you do a precipitation reaction. So let's take a look at a little bit of stoichiometry here. So often we have to solve stoichiometry problems. This is kind of a big part of Unit 4. We have an equation given to us here. And it says in a chemical analysis, excess silver ions are added to a solution containing carbonate ions. After the reaction, the total amount of silver carbonate solid is weighed and found to have a mass of 0.582 grams. How many grams of carbonate ions were present in the original sample? Well, what we have to do here is start out with the 0.582 grams of silver carbonate. And the question is asking how many grams of carbonate did we have starting out? So way down here at the end, I'm going to write grams of carbonate down here. And whenever we have a stoichiometry process, I always tell my students we have a 3-step process here. Step 1 is convert to moles. Step 2 is do the mole ratio. And step 3 is convert to whatever your final unit is. In this case, it's looking like it's going to be grams. So step 1, convert to moles. So that means in our denominator, we have to put grams down here, so it'll cancel, and moles on top. Now, we can consult the periodic table, and we can see that 1 mole of silver carbonate, Ag2CO3, has a mass of about 275.75 grams. So we can cancel grams top and bottom, and we're in moles of silver carbonate. Now we can go on to step 2, which is the mole ratio. So the mole ratio is where we take the actual substances out of the equation here and put them into our stoichiometry here. So Ag2CO3 has to go on the bottom, so it'll cancel out. We're converting to carbonates ions, so those will go on top. And now it looks like we have 1 carbonate for every 1 silver carbonate. Those are just the coefficients of the balanced equation. So now silver carbonate goes out top and bottom. We're in moles of carbonate. We want to be in grams of carbonate. So step 3 is convert to that final unit, which is grams. So moles on the bottom and grams on top. So according to the periodic table, it's about 60.01 grams in 1 mole of CO3, 2 negative. So moles are out. And so on my calculator, I just take 0.582 divide by 275.75 times 60.01, all these ones kind of cancel out, and I find that the answer is about 0.127 grams of the carbonate ions right there. So that's how you would do a fairly simple stoichiometry problem. Now, let's try another one. Let's try one where we have some solution stoichiometry, because they do like to ask these on the exam, and sometimes this throws off a lot of students because of these units that we use. So in this problem, it's the same equation, but this time it says a student adds 100 milliliters of 0.100 molar silver nitrate to a solution of excess sodium carbonate. Assuming the reaction goes to completion, how many moles of silver carbonate should be produced? So the first thing I want to do is I want to figure out how many moles of the silver ions did we use. Because the problem gives me enough information to figure out. I have 0.1 liters, and I have zero point 0.1 moles per liter. So to find the moles, you just take the molarity times the liter. So 0.1 molar times 0.1 liters is 0.01 moles of silver ions. So that's what I'm going to start with, the 0.0100 moles of silver ions. And the question is, how many moles of silver carbonate should be produced? So that's what I'm going to put down here at the end of my stoichiometry process. So essentially, right now, I just have to do a mole ratio because, step one is convert to moles, and I'm in moles right now. So I can put Ag plus on the bottom, and Ag2CO3 goes on the top. And looking at the equation to do the mole ratio, it's 1 silver carbonate for every 2 silver ions. And so now I just have to divide 0.0100 divided by 2, and the answer is about 5 times 10 to the negative third moles of silver carbonate, or 0.00500 if you prefer that. So those are some fairly straightforward stoichiometry problems. Make sure that you're able to do those. Now there are others that you might want to learn how to do, or perhaps I should say relearn or remember how to do, like limiting reactant problems, percent yield. I have videos for all of those as well. Let's go on to Unit 5, which is kinetics, and so the concept of rate. Probably the most important thing that you need to know how to do as far as kinetics goes is know how to write a rate law and understand how to find the order of a reaction with respect to a specific reactant. You're going to see some sort of a table like this on your exam somewhere where you'll have a balanced equation and you'll have these multiple trials, and we're trying to figure out the orders and the rate laws and things like that. So the first part of this says, find the order of the reaction with respect to nitrogen dioxide. What we have to do here is find 2 trials where nitrogen dioxide is the only thing that's changing in the experiment. So it looks like experiments 1 and 2 are going to fit the bill here because fluorine is being held constant from trials 1 to 2, and looks like NO2 is being doubled. So it goes from 0.01 to 0.02. And notice that while that's happening, the rate is doubling as well. The 2.37 times 10 to the minus third is doubling to 4.73 times 10 to the minus third. So 2 equals 2. And what's the power that makes this a true statement? Well, it's a power of 1. So that means we say that this is a first order process with respect to nitrogen dioxide. If we had doubled the concentration but the rate had quadrupled, well, that would have been a second order process. Or if we had doubled the concentration and the rate hadn't changed at all, that would have been a 0th order process. Now let's do the same thing but for F2 this time. And this time I'm going to choose trials 1 and 3 because it looks like from trials 1 to 3, NO2 is being held constant this time, and fluorine is the one that's changing. Except this time, it's not being doubled, it's being tripled. 0.01 to 0.03, it's being tripled, and looks like the rate is being tripled as well from trials 1 to 3. So that's a first order process as well. So it's first order with respect to both of the reactants. And if the question ever asks you what is the overall order, well, it's just the sum of the individual orders. So 1 plus 1 is 2. So that means it's overall second order in this process. Now, let's take this a step further. Let's write the rate law. So if we write the rate law for this reaction, it's always written in the format rate equals K times the concentration of the first reactant, which is NO2, raised to its order, which is 1, so that's why there's no visible exponent here, times the next reactant, which is F2, raised to its power, which is a 1 as well. Now I want you to notice that in order to write a rate law, you have to have some sort of data. Have to have some sort of data like experiments here, perhaps a mechanism. You can't just look at an overall balanced equation and guess what the rate law is. We can't say, some students might say, well, there's a 2 right here in front of NO2, so why isn't it second order? Well, it doesn't work that way, okay? You have to have some sort of experimental data in order to write a rate law. So that's why it's first order in both of these. Now, let's take it a step further. let's determine the rate constant for the reaction at this temperature. Well, what we have to do here is take any of these trials. It doesn't matter which trial you use, 1, 2, or 3, but take the data from that trial and plug and chug into the rate law. Now, I'm going to use trial 1 just because it has a bunch of 1s in it and it's kind of convenient to use, but I'm going to plug those numbers into the rate law here. So the rate in trial 1 is 2.37 times 10 to the negative third molar per second. Now the K is what we're solving for, so that's my unknown. The concentration of NO2 in trial 1 seems to be 0.010 moles per liter, and the concentration of F2 in that trial is also 0.010 moles per liter. So now all I have to do is solve for K. Now the calculating part of this is pretty easy. We find that K is about 23.7. On these questions, they really want you to make sure that you have the correct unit. And the units are a little tricky here. So that's why I want to lead you through this. So to get the units, I want you to notice that we have to isolate the unknown, which is K. So we have a molarity times a molarity left over here. So in order to get rid of that, I'm going to multiply that by a molarity to the negative 2. Okay, that's going to get rid of your 2 molarities there. And in order to make that work, if I do something to one side of the equation, I have to do the same thing to the other side of the equation. So over here, I'm going to also multiply by molarity to the minus 2. Now, this molarity that's here times molarity to the minus 2 gives me molarity to the minus 1. So that's why my units are molarity to the minus 1 times seconds to the minus 1 when I drag the seconds back up to the numerator. Okay, so that's my appropriate rate constant with units. When you have this, you got to make sure you have the right unit in there. It's a little tricky, so make sure that you do that. Okay. Now, another way to determine the order with respect to a reactant is to do this graphically. So let's say we have a reaction. So here's we have 2Ni yields H2 and I2, and we've decided to graph these values here as a function of time. On one graph, we have the concentration versus time. On another graph, we have the natural log of concentration versus time. And on yet another graph, we have 1 over the concentration versus time. So how do we find the order of the reaction with respect to HI? Well, here's how it works. If the order is 0 order, then the concentration versus time graph would be a straight line. Well, it's not. This is a curve, so it's not 0 order. If it's a first order process, the natural log of concentration versus time is going to be a straight line. That's a little straighter, but it's still not straight, is it? So it's not first order. If it's a second order process, the graph of 1 over concentration versus time is going to be a straight line. And that is a straight line. So that's why I would say it's a second order process. Now, as it turns out, this is the only reactant in the reaction. So writing the rate law is pretty easy at this point. It's just rate equals K times HI to the second power because it's second order. So that's how you can determine this graphically. They're probably going to have that on the exam at some point as well. So make sure that you can solve something like that. Now, how could you determine the rate constant? Well, to determine the rate constant, you just look at those 3 graphs and look at the one or focus on the one that's a straight line. So that would be the 1 over HI graph in this case. So you want to find the slope of that line. Okay? The absolute value of the slope is equal to the rate constant. Okay? That's all you got to do. And I say absolute value because notice that the HI and the natural log of HI, those are sloping downward. And so if you have a slope of those lines, it's going to be a negative value. And rate constants are always positive, so that's why I say absolute value. That works for this as well. Of course, it's a positive slope anyway, but that still works. So to find the rate constant, it's just the absolute value of the slope of the straight line. Okay. Now, another important thing to know how to do in kinetics is work with reaction mechanism. So if we have a mechanism for a chemical reaction, and this is what you have here, we need to realize that there are often reaction intermediates. Notice that there's a little substance here, this BF2, that's produced in an early step, and then it's used up in a later step. So when you add these equations or these steps together, you end up canceling them out. Okay, that's the reaction intermediate. The BF2 is the reaction intermediate. It's essentially used up about as fast as it's produced. And so this is kind of hard to isolate and to measure very easily. Now, what's the overall balanced equation? Well, this is the point where you just have to add those two together. So we have BF3 plus 2 O2s get us boron plus O2F2 plus O2F. And so there's the overall balanced equation. Now, often we're given a little bit of extra information. And notice that I just put on the board here that the first step is a slow step and the second step is a faster step. Perhaps there's an equilibrium here. I don't have that drawn in, but it's often how it works. So which one is the rate determining step? Well, the slow step is always the rate determining step. So in this case, it's the first step. And why? Well, because it's the slow step, and that's how that works. Now, what is the overall rate law for the reaction? Well, the rate law for the overall reaction is the same as the rate law for the slow step. And so the way you write that is just rate equals K times the concentration of the first reactant of that slow step times the concentration of that other reactant in that slow step as well. So it's going to be rate equals K times BF3 concentration times O2 concentration. And that's basically all you have to do for that one right there. Okay, so that's a simple review of reaction mechanisms and how to write rate laws there. There are some more things you might need to be able to do, but I have a video for that if you want to go more in depth into mechanisms. Now, let's go on to Unit 6, which is about thermodynamics, and specifically the first law of thermodynamics. And let's say we have a question like this. A student adds 0.500 grams of warm copper metal to a 52.77 gram sample of water. After stirring, the temperature of the copper metal drops from 356.0 degrees Celsius down to 23.0 degrees Celsius. The specific heat capacity of copper metal is 0.385 joules per gram degree Celsius, and the specific heat capacity for water is 4.18 joules per gram degree Celsius. Assume that no heat is lost to the surroundings. So the first question I have for you here is, how many joules of heat were lost by the copper? Well, anytime we have a problem that talks about specific heat and we're dropping something in and there's a mass and something like that, we're going to use Q equals mc delta T. So once again, this is just a plug and chug. We're trying to solve for Q, which is joules, so we're going to solve for that. The mass of the copper is 0.500 grams, so that goes in for M. C is specific heat capacity. So the specific heat capacity of copper is the 0.385 joules per gram degree Celsius. And notice that the temperature of the copper drops from 356 degrees down to 23.0 degrees. So when you subtract that, I think that's about 333 degrees Celsius. Notice it's a drop in temperature, so that's why I have a negative value here. Now, when you use your calculator and multiply these together, you find that it's about negative 64.1 joules. And that negative sign just implies that heat has been lost. So that means we can safely say that about 64.1 joules of heat were lost by the copper. Now, if that's the case, how many joules of heat are gained by the water? Well, we're assuming that no heat is lost to the surroundings, so that means that whatever heat was lost by the copper is going to have to be the same as the amount of heat that's picked up by the water. So that means that the heat gain by the water is 64.1 joules, so it's just the same amount. Now, what was the original temperature of the water? Well, we're going to use the same equation, Q equals mc delta T. Now this time, we know how many joules were picked up by the water. It was 64.1 joules right out of the problem here. The mass of the water, the M, it's up here. It's about 52.77 grams. So that goes in there for M. C is your specific heat capacity, which is 4.18 joules per gram degree Celsius. And delta T is your change of temperature. And that's what we're solving for here. It says, what was that original temperature? We're going to solve for delta T. So when you key this into your calculator, you find that delta T is about 0.29 degrees Celsius. Now that means that the water temperature went up by about 0.29 degrees Celsius. Now let's reason through this. If the temperature of the water ended up at 23 degrees Celsius, and we know that because when you take something that's hot and you drop it into something that's cold, the hot object is going to drop in temperature, the cold object is going to rise in temperature, and their final temperatures will both be the same, won't they? So that means that if copper's final temperature was 23 degrees, water's final temperature had to be 23 degrees as well, right? So if it ended up at 23 degrees and it rose by 0.29, what was its initial temperature? Well, it has to be about 0.29 less than that. So that's why we can safely say that the original temperature of the water was about 22.7 degrees. So that's your initial temperature. I'm trying to use a proper number of sig figs as much as I can because we didn't have the original temperature out to the hundredths place on that one. So that's why I said 22.7 degrees. Now, as we heat something up, speaking of heating things, we can take a material or a substance and we can heat it up. And if it starts out as a solid, its temperature is going to rise. Just like we have here as we add heat. Its temperature rises, and anytime you have just an object that's in a specific state of matter, its temperature goes up whenever you add heat to it. However, once it gets to a phase change, when you add heat, its temperature stays level. So notice that as we get to the melting point of whatever this substance is, it just stays constant. And the value that goes along with that is the heat of fusion, or the enthalpy of fusion. Okay? Once it's all melted and it's all a liquid and you add heat, well then it keeps going up again. Okay, so its temperature goes up until it hits the boiling point, and then you add heat and it levels out. Until all the substance is boiled away, you keep adding heat, then it goes up as a gas and its temperature goes up again. Now you can do this in reverse. It would be called a cooling curve. If you start out at a high temperature and you're getting cooler, that would be called a cooling curve. Now, speaking of enthalpies and heats, let's say we have this reaction here. And let's work with enthalpies of formation a little bit because they often like to ask you something like this on the exam. And let's say that we know that the change in enthalpy for this reaction is 16.38 kilojoules per mole of reaction. And the question asks us to determine the enthalpy of reaction of N2O. Okay? And somewhere they're going to have to tell us the enthalpy of reaction of NO and N2 in order for us to figure this out. Well, if that's the case, we don't know what N2O is, so we're going to call it X, and we have 2 moles of this. So that means we have to multiply it by 2. And 2 times X, of course, is just 2X. They're going to have to tell us somewhere on the exam what the enthalpy of formation of nitrogen monoxide is. So it's about 90.29, and we have 2 moles of that as well. So we have to times that by 2. So that's where we get 180.58 kilojoules. And nitrogen gas is a 0. And just in case they don't tell you this, any element, any freestanding element in its most natural state has an enthalpy of formation of 0. Okay, so they may tell you this, they may not, but just be aware it's 0. There's only 1 mole of that, so that's still 0 kilojoules. And the way this works is the delta H of the reaction is equal to the sum of the products minus the sum of the reactants. Okay, so the sum of the reactants, well, we just have a 2x there, so we'll deal with that in a second. The sum of the products, 180.58 plus 0 is 180.58 kilojoules. And the delta H of a reaction is the sum of the products minus the sum of the reactants. And so that means I have to take the delta H, which is 16.38, given to us in the problem, equals the 180.58 minus 2x. And if I can solve for x, I'm going to find the enthalpy of formation of the N2O. So just use some algebra here. Subtract 180.58 from both sides and divide by -2. And I find that X is about 82.1 kilojoules per mole. So that would be my enthalpy of formation of N2O. Sometimes they give you an easier problem where they just give you the enthalpies of formation of all of these substances, and you just have to plug them in and find the delta H for the whole reaction. But on the exam, on the AP exam, sometimes they like to throw you a curveball and do something like this. So that's why I wanted to work a problem like this for you. Let's say we have equilibrium. Let's go on to unit 7 here, which is equilibrium. And a very important skill, a very fundamental skill actually, is being able to write equilibrium constant expressions for pretty much any reaction. And remember, it's written by taking products over reactants raised to the power of the coefficients. And you're going to want to omit any liquids or solids that are given to you in the problem. You only have gases and aqueous substances in the expression. So in this one here, notice we have a couple of solids, and so we have to ignore those, or at least omit them from the equilibrium constant expression. If we're going to write this in terms of concentration, that's called Kc. And you would write these in brackets. And so the brackets imply the molarity of the solution or the substance. So Kc equals the concentration of the aluminum ions over the concentration of the silver ions cubed. And once again, that cubed is because there's a little 3 as a coefficient right there. Now sometimes we're given a reaction that has all gases, and in that case it's a lot more convenient to measure this in terms of pressures or partial pressures, and we call that Kp. In that case, you'd write it more like this, where Kp equals the partial pressure of NO squared, and notice that squared comes from the fact that there's a coefficient of 2, times the partial pressure of nitrogen, all over the partial pressure of dinitrogen monoxide squared. And once again, the squared comes from that coefficient of 2 right there. So be able to write an equilibrium constant expression. Now, let's solve a problem. Here we have that very same problem that I think we just looked at, or that same equation. It says at a certain temperature, the reaction below occurs, and a chemist investigates the process by filling a container with dinitrogen monoxide gas to a pressure of 1 atmosphere. After the mixture attains equilibrium, the pressure of dinitrogen monoxide gas has dropped to 0.80 atmospheres. Calculate the equilibrium constant, Kp, at this temperature. So all we have to do here is set up an ice box. I strongly recommend that if you have an initial pressure or concentration and final, there's a lot going on here. So use an ice box. And so the initial pressure of N2O is 1 atmosphere. So that goes in right here in that position. And it says that's all that's put in there. So we can safely assume that the initial pressures of your products are both going to be 0, unless it says otherwise. Now, it also tells us that once you get to equilibrium, the pressure of N2O is down to 0.80 atmospheres. So for equilibrium, N2O, I'm going to put in 0.80 atmospheres. Now notice, that's all that's given to us. But guess what? That's enough to solve the puzzle. We can figure out what every other slot in that icebox is going to be. So let's start by realizing that the 1 to 0.8, that's a drop of negative 0.2 atmospheres. Now on the other side of the reaction, if N2O is going down, then the products have to be going up. That's how chemical reactions work. And since this is a 2 to 2 ratio, well, the nitrogen monoxide is going up by the same amount that the N2O went down. So that's why the NO is a plus 0.20. And since it's a 2 to 1 ratio, N2 is going up by half as much. So this is a 0.10. So our equilibrium pressures are 0.20 and 0.10. And so now I just have to take these equilibrium values and plug them into the equilibrium constant expression. Now I have to write that. It's the same as it was earlier whenever we wrote that on the last slide here. It's the pressure of NO squared times N2 all over N2O squared. And I just plug those numbers into each appropriate slot, like this, 0.2 squared times 0.1 all over 0.8 squared, and I find that the Kp value is equal to 6.3 times 10 to the negative third. Remember, equilibrium constants have no units. Now, one thing I might notice is this Kp value is kind of a small number, isn't it? Anytime you have a small value, as in like way less than 1, okay, that means you're going to have a whole lot of reactants and not very many products. Okay, that's just how that works. If you have a very large value of K, like 1,000,000 or 1,000,000,000 or something like that, something much greater than 1, it's going to be the opposite. You'll have a whole lot of products and not very much reactant left over. So be able to interpret the meaning of an equilibrium constant as well. Now, as we move on, let's say we have another problem. At the same temperature as the previous example, a mixture of these three gases is what that should say, that these three gases was added to a closed container. The partial pressure of N2O gas was 1.35 atmospheres, the partial pressure of NO gas was 0.20 atmospheres, and the partial pressure of N2 gas was 0.3 atmospheres. What is the total pressure in the container? Well, we have to understand that the total pressure is just the sum of the individual partial pressures. So we have to take that, that 1.35, the 0.20, and the 0.30 and add them together, and you'll find that the total pressure in the container is 1.85 atmospheres. Now, the next part of the question says, as the reaction proceeds, which gases will increase in pressure and which gases will decrease in pressure? Now, this is a very typical example of a reaction quotient question, what we call Q versus K. We don't know if this mixture here is at equilibrium or not. And so we have to plug this into the reaction quotient expression. And it's written exactly the same as the K expression. We just can't call it K because we don't know if it's at equilibrium or not. So we call it Q. So we have the same expression I wrote before, except I'm calling it Q. And I'm going to plug those same pressures into the expression. So I plug in, the 0.20 is the NO, so that gets plugged in there. The N2 is 0.30, so that's plugged in there. And the N2O is 1.35, so it gets plugged in there. And I find that the value for Q, once I mathematically calculate that, is about 6.6 times 10 to the negative third. And once I get the Q, I compare that to the equilibrium constant. Now, I'm at the same temperature as I was in the previous example, so the equilibrium constant's the same. So the Q is 6.6 times 10 to the negative 3. The K is 6.3 times 10 to the negative 3. So it looks like Q is a little bit greater than K. Now, what does that mean? Students get this confused sometimes. So what I like to do is I draw in a little Pac-Man here. So if I do this, I can see that the Pac-Man is eating toward the left. Okay? If it's eating toward the left, that means that as it goes toward the left there, it's going to be going toward the side of the left, which is the reactant side. So that means the reactant side is going to predominate. It's going to increase. So I would expect that the N2O is going to go up. And it's going to do that at the expense of the other side, which is NO and N2. So the NO and the N2 are going to go down. Okay, so that's how you would solve these Q versus K problems. And sometimes they're in a little bit of a disguise, kind of like you have here. It doesn't say toward which side does it go. It just says which gases are going to go up, which side is going to go down. So this is a good Q versus K problem. Now, how about this one here? After the reaction has returned to equilibrium, how would each of the following changes affect the partial pressure of nitrogen gas in the reaction vessel? So this is a Le Chatelier's principal question. If we add some NO right here, anytime you add something, it's going to go toward the other side. So in this case, we're adding a product, so it's going to go toward the reactant side. So the N2O is going to go up, and the N2 will have to go down in response. So that's why the N2 decreases. How about if we take away some N2O? Okay, well, if we take away something, the reaction is going to shift in such a way to replenish whatever was taken away. So whatever we took away is actually going to go back up. So if we take away N2O, then the N2O is going to increase, right? And it's going to do that at the expense of the other side. So guess what? The N2 is also going to decrease. Okay, what about if we add some helium gas? Well, helium gas has nothing to do with this problem, does it? It is an irrelevant, inert gas, and so there's going to be no change if we add some helium. They like to ask you that sometimes, and some students get tripped up on that, but don't let that trick you. It's no change if it's an inert gas that doesn't have anything to do with the reaction. What about if the pressure is decreased by increasing the volume? Okay, well, whenever you increase the volume of a container, the equilibrium is going to shift toward whichever side has more moles of gas, because that's the side that takes up more space. Well, in this case, we have 2 moles of gas on the reactant side, and we have 3 moles of gas, 2 plus 1, on the product side. So whenever we increase the volume, in this case, it's going to go toward the product side. And N2 is a product, so we're going to have N2 increasing. So that's the result for that one. How about what if the temperature of the container is increased? Well, this is why we use our delta H in here. Notice that the delta H is positive. So that means this is an endothermic process, right? So that means that heat is acting as a reactant, as it is in every endothermic process. So when you increase the temperature, we're adding heat, aren't we? So that's like adding a reactant. So it's going to shift toward the other side. So when you add heat, it's going to shift toward the product side, isn't it? So N2 is going to increase as well. So be aware of how these different changes, these shifts, are going to affect things using Le Chatelier's principle. Now, let's take a look at Unit 8, which is acids and bases. And let's think about the relationships between hydronium ions and hydroxide ions, as well as pH and pOH. Now, this is probably the fundamental equation here. The hydronium ion concentration times the hydroxide ion concentration for any solution is always equal to Kw. Okay? Now, at 25 degrees Celsius, it's kind of nice that Kw works out to this nice round number. It's 1.0 times 10 to the negative 14th. So that means that as long as you're at 25 degrees Celsius, the hydronium ion concentration times the hydroxide ion concentration equals 1.0 times 10 to the negative 14th. So if you know one of these, you can calculate the other. And then to add on to that, we have these other equations. pH is equal to the negative log of the hydronium ion concentration. And likewise, pOH is the negative log of the hydroxide ion concentration. I don't have it on the screen, but pH plus pOH equals 14. Okay, that's kind of a different way of stating this one here, but pH plus pOH equals 14. So let's try this problem here. At 25 degrees Celsius, a solution has a pH of 9.58. Determine its pOH, its hydronium ion concentration, and its hydroxide ion concentration. Well, we'll do the easy one first. Let's find the pOH. If pH plus pOH equals 14, well, all we have to do to find the pOH is subtract the pH from 14. So 14 minus 9.58 gets us about 4.42. So that's the pOH of this solution. Let's do the next one, the hydronium ion concentration. Well, if we know the pH, we can figure out the hydronium ion concentration by taking the negative antilog of the pH. That just means we take 10 to the negative pH power. So 10 to the negative 9.58 is a concentration of 2.6 times 10 to the negative 10th. So that's the concentration of hydronium. And if you want to find the hydroxide concentration, well, there are a couple different ways to do that. We could take, we could use this equation here. Take H3O plus times OH minus yields Kw, or we could also do this. We could take hydroxide equals 10 to the negative POH power. And so hydroxide is 10 to the negative 4.42, we got back in the first part of this. And so the hydroxide is equal to 3.8 times 10 to the negative fifth moles per liter. Okay, so moles per liter are the units on both of those there. Now, just to check your work, if you want to, if you take the hydronium ion concentration times hydroxide ion concentration, you should get a number that's very, very close to 1 times 10 to the negative 14th. So we have that. Now, let's think about strong acids and strong bases for a few minutes here. There are 6 strong acids. You need to know those. And for those 6 strong acids, the concentration of that acid is equal to its hydronium ion concentration. So if you want to find the pH of a strong acid, it's really easy. Just take the negative log of its concentration. So for example, if we have 0.25 moles per liter of nitric acid, all we have to do to find the pH is just take negative log of 0.25. And you find that that pH is 0.60. Pretty simple. Okay. For strong bases, it's fairly straightforward as well. There's a little extra step in there. There are 8 strong bases, essentially the group 1 and 2 hydroxides. It's done the same way. The concentration of the compound is equal to the hydroxide concentration. Just be aware that on the group 2s, we have a 2-to-1 ratio, so you have to multiply by 2. So if we have 0.25 molar calcium hydroxide, well, the hydroxide concentration is 0.50. And so to find POH this time, it's negative log of 0.50. And that means our POH is 0.30, and the pH, 14 minus that, is 13.70. So that's how you find the pH of a strong acid or a strong base. What if it's a weak acid or a weak base? Well, we have to consider that this is an equilibrium problem, essentially because weak acids and weak bases don't dissociate all the way. We have to work these out as equilibrium. So let's try a fairly straightforward weak acid problem here. It says determine the pH of 1.25 moles per liter acetic acid. And it gives us the Ka. That Ka is 1.8 times 10 to the negative fifth. And so the first thing you want to do here is write the dissociation for this, write the equation for it. And so we have our weak acid, the acetic acid. It's being added to water. Now, anytime we have an acid-base reaction like this, an acid is always reacting with a base, right? So if this is a weak acid, that means that water is acting as a weak base here, okay? Now, as we think about the products, well, the acid is a proton donor, and the base is a proton acceptor, right? Well, once that water has accepted the proton or accepted the H+, it becomes H3O+, hydronium, which makes sense because this is an acid problem, right? And likewise, that acetic acid, once it's donated that proton, donated that H+, all that's left is the acetate ion, okay? So notice we have 2 conjugate acid-base pairs. The acetic acid and the acetate ion are a conjugate acid-base pair here. And likewise, the hydronium and the water make a conjugate acid-base pair as well. So you may be asked that. In fact, I'm pretty sure you will be asked that at some point on the exam to identify conjugate acid-base pairs. Now let's go back to the problem here. Let's set up the icebox. And so our concentration of the acid is 1.25 moles per liter. So that goes here. And then the hydronium and acetate ions are essentially 0. We don't know the change, so we know that this acetic acid has to go down by x, and the products have to go up by the same amount, which is x. And so at equilibrium, we have 1.25 minus x, x, and x. So we're going to plug these values into the equilibrium constant expression. So we write that like this. Ka equals hydronium ion concentration times acetate concentration all over the acetic acid. Notice that liquids like water are not in this. So we just plug and chug. The Ka is 1.8 times 10 to the negative fifth equals x times x over 1.25 minus x. Now, a little mathematical trick that we do often in these problems is when we realize that this is a small equilibrium constant, we're going to go ahead and ignore the minus x there to make our math a little bit easier. And we can cross multiply, and you find that x squared equals 1.25 times 1.8 times 10 to the negative fifth, which is x squared equals 2.25 times 10 to the negative fifth. Take the square root, and x, which is equal to the hydronium ion concentration, is 4.74 times 10 to the negative third moles per liter. And to find the pH, we just take the negative log of that number. So the pH here is 2.324. And so makes sense. It's an acidic pH. It should have a pH much less than 7, shouldn't it? Now, let's do one little calculation here. Let's calculate the percent dissociation. So the percent dissociation is where you take the hydronium ion concentration. In the case of a weak base, it would be the hydroxide concentration, but it's hydronium here, divided by the initial concentration of the substance, which is 1.25. Of course, times 100. I ran out of room here, so that's why I didn't put the times 100. But when you find the percent dissociation, it's about 0.379% dissociated. And that makes sense because this is a weak acid. You would expect it to have a fairly or a very low percent dissociation. Now, let's talk about acid-base titrations for a couple minutes. We know that the goal of a titration is normally to determine how concentrated an acid or a base is. So whenever we take a titration, if we plot the volume of a substance that's added, usually the base, on the x-axis, and we plot the pH on the y-axis, we can get this curve, this graph here. This is called a titration curve. And there's some interesting data that we can get out of this titration curve. Now, let's take a look at the first question here. Let's say that if we have 10.00 milliliters of a weak acid that was used in this titration, determine the acid's concentration. Well, we're going to plug this into the titration equation. Molarity of the acid times volume of the acid equals molarity of the base times the volume of the base. So molarity of the acid is what we're trying to solve for. So Ma is the unknown. The volume of the acid, what it says right here, we use 10.00 milliliters. So that goes in for Va. Now the molarity of the base is given to us in the graph. It says that the base is 0.100 molar. So that goes in for M sub B. And then the volume of the base, well, notice that there's this inflection point right here, right around the 25 milliliter point. That tells me that was the point where we got to the equivalence point. So that means that VB is 25 milliliters. So I put that in right here. I can solve for M sub A using simple algebra, and I find that it was 0.25 moles per liter of the acid. So using that titration equation in this curve, we can get some pretty good information there. Now, let's estimate the Ka of the weak acid used in this titration. Well, the way we do that is we have to find the half equivalence point. So notice that it took us 25 milliliters to get to the equivalence point. Well, the halfway point would be 12.5. So I go to the 12.5 milliliter point, which is right here. Looks like it's marked V. And at that point, pH equals pKa. And so the pKa, let's see, that pH is about somewhere around 5.4 if we just kind of eyeball that. So that means that the Ka is 10 to the negative 5.4, which is very close to 4.0 times 10 to the negative 6. And so that's how you can use a titration curve to estimate the Ka, or the pKa also, of the acid that you're using. Now, let's go back to this titration curve, and let's try to analyze the primary reaction component, other than water, of course, that's present in the titration flask at each of the following points. Well, at point V, that's the halfway point. You need to realize that at that halfway point, you have the same amount of acid as you have of the conjugate base. Now, we don't know what the acid is, so I'm just going to use the generic HA here. But whatever it is, the HA and the conjugate base of that acid, A negative, are going to have equal concentration. So it's actually a tie at point V. Now at point W, we've added, as you notice, we've continued to add the base, and so the base, the conjugate base anyway, is going to predominate at point W. So as the pH is rising faster, we have more of the conjugate base than we have of the weak acid. So the A negative is our primary component at that point, even though we do still have a fairly significant amount of the weak acid. Now, once you get to point X, that is the equivalence point, and your acid is all gone at that point. And so all you have left is just A negative. So all you have, other than water, of course, in the flask, is the conjugate base at the equivalence point. Now, once you go past that and you have essentially overshot your titration, you have an excess of hydroxide as you keep just pouring in the hydroxide, and that's why the pH just keeps shooting up so fast after that equivalence point. So that's why hydroxide is your primary component once you've overshot the titration at both points Y and Z. Now, let's go on to Unit 9 and talk about thermodynamics, and specifically the second law of thermodynamics in the first part of this. Now, when we talk about the concept of entropy, we need to understand that there are a couple different ways of talking about this. Entropy, if you look it up in the dictionary, says it's a measure of the total number of possible energy states in a material. And that is a very good definition. We sometimes say it's also how well something is dispersed. That's also a very good definition. I found that students sometimes find it easier to think of it in terms of disorder or chaos. Entropy is a measure of the disorder in a material. So if you think about it in terms of that, you're gonna it might be easier for us to kind of reason about it in that way as well. So if you have a solid, not much disorder there. Everything is crystalline. It is in this nice orderly fashion. So you have very little entropy in a solid. So solid has the least entropy. As you move up in entropy and have a liquid, you have molecules that are able to move around freely. They're slipping and sliding around each other. So liquids have more entropy. If you have an aqueous solution, you have that liquid, but now there's even more disorder because we have these ions or perhaps these other molecules that are swimming around in the liquid. So that has even more entropy. And once you get to a gas, well, every molecule is independent of each other. So gases have the most entropy if you're comparing solid, liquid, aqueous, and gas. And so that's the hierarchy of entropy. If everything is at the same state, then we can say that materials at a higher temperature are going to have more entropy than substances that are at lower temperatures. And that makes sense because your molecules are moving around faster at higher temperatures. So that sounds like more disorder, doesn't it? If it's a tie and you're at the same temperature, well, a container that has more molecules is going to have more entropy than those with fewer molecules. So if everything else is the same, you have the same temperature, the same state of matter, and you have a container with 10 molecules or 10 moles, it's going to have more entropy than a container with 3 molecules or 3 moles. And so more molecules implies more entropy. So let's predict the sign for the change in entropy, delta S, for each of these processes. Well, in this first one, we have a gas, actually 2 gases, that are changing into a solid. So a gas down to a solid, that's a drop in entropy. So that's why it's a negative delta H for that one. What about this one? Here we have a solid that's changing to a gas. Well, solids have a low entropy, gases have a higher entropy. So that's an increase in entropy, increase in delta H. How about this one here? We have 2 ions that are aqueous, they're swimming around in solution, and they end up turning into a solid. Well, aqueous has a fairly high entropy, and solids have the lowest, don't they? So that's a drop in entropy, negative sign of delta S. How about this one? Well, here we don't have any change in state, do we? They're all gases here, so the tiebreaker is how many molecules do we have? So notice that in this one we have 2 molecules of gas on the left and 2 plus 1. So that's 3 molecules of gas on the right. So if it goes from 2 to 3, that's an increase in entropy, isn't it? So that's why the sign for that reaction is a positive delta S. So you should be able to predict the signs of delta S just by looking at a chemical reaction for pretty much every reaction that you could encounter. Now, will a reaction take place? Well, when you answer that question, you're saying if a reaction is thermodynamically favorable. Now, as we think about this, there are basically two forces that are going to determine if a reaction is thermodynamically favored. The first one is enthalpy. Now, we talked about that a little bit earlier. We said that enthalpy is delta H. That's the heat, right? And we find that exothermic reactions tend to be favored by the universe. It's almost like the universe likes exothermic reactions. So if something is exothermic, that's something in its favor. There's a good chance that at least at some condition, it's going to be thermodynamically favorable. And the other process, or the other force, I should say, is entropy. Now, we find that processes that have an increase in entropy tend to be favored by the universe. So if you look at a reaction and its sign for delta S is positive, then there's a good chance it's going to be thermodynamically favored, at least under some conditions. If you ever find a reaction that is both exothermic and has increasing entropy, it's going to be favored at all temperatures. Okay? It's just at all temperatures, always thermodynamically favorable. However, if it's the opposite of that, if it's an endothermic reaction and it has a decreasing entropy, then that reaction is never going to be thermodynamically favored under any condition. So we have that. Now, if only one of the factors is favorable, the process will be thermodynamically favored only at certain temperatures. So that means that if you have a reaction that is endothermic, delta H positive, and it's increasing in entropy, delta S positive, it's going to be favorable at high temperatures. They're both positive. At very positive temperatures, it'll be favorable. If it's the other direction, if they're both negative, it's exothermic, and the entropy is decreasing, it's going to be favorable at lower temperatures. Now, as we talk about this business of thermodynamic favorability, we know that that is Gibbs free energy. Delta G is kind of a numerical way of calculating or determining or talking about thermodynamic favorability. And there are a couple different ways to calculate thermodynamic favorability. The two probably most common ones are shown here. We can calculate it by saying delta G equals the delta H of a reaction minus its temperature in kelvins times its change in entropy. You can calculate delta G. If you know the equilibrium constant, you can figure it out as well. Delta G equals negative R, which is 8.314 joules per mole per Kelvin, times the temperature in kelvins, times the natural log of the equilibrium constant. So you can find the delta G in a couple different ways here. And there's another one that we talk about in our daily lessons as well. If you have the delta G, Gibbs free energy, that is a positive number, it's not thermodynamically favored. If it's negative, it is thermodynamically favored. So that's just a little quick review of thermodynamic favorability and the second law of thermodynamics. As we wrap things up in Unit 9, we want to talk about galvanic cells. Galvanic cells, or sometimes called the voltaic cells, are basically just batteries. These are thermodynamically favored processes where we have an oxidation-reduction reaction taking place, and we're harnessing it to power some sort of a load, like maybe a light bulb or a cell phone or something like that. And whenever we have this, we have to have two different electrodes. We have a wire here. We have ions in solution that are corresponding to what's in the electrodes there. And we have a salt bridge. Now, every half reaction, as we look it up in our data tables or in our chemistry textbook or what's given to you on the AP exam, it's going to be given to you as a reduction half reaction. So as you think about the silver here, we would write it as the silver ions are being reduced into silver metal by that half reaction right there. And its half potential, I should say, is positive 0.80 volts. And we can say the same thing for aluminum ions. Aluminum plus 3 being reduced down to aluminum by means of 3 electrons would be negative 1.66 volts. Now, I guess the main question here is which one is the cathode, which one is the anode? Well, the way we do this is we use this reaction or this equation right here. E cell equals E cathode minus E of the anode. And this reaction or this equation is not given to you on the AP exam. You have to remember this one. And E cell, the overall cell potential or voltage, has to be positive, which means we have to arrange these two numbers in the equation in such a way that we get a positive number. And the only way to do that is to arrange it like this, with the plus 0.80 in the cathode position and the negative 1.66 in the anode position. So when you calculate this, you find that the E cell is 2.46 volts. So that's the voltage that's going through this wire here, as long as we're at standard conditions, which is 1 mole per liter and 25 degrees Celsius and all that. Now, that also tells us that 0.80, which is the silver, well, that's the cathode. And the cathode is where reduction is taking place. So yes, the silver is being reduced into silver metal here. The silver ions, I should say, reduced into silver metal. That means that the aluminum is where the oxidation is taking place. That's called the anode, which means whenever we write the overall balanced equation, we have to flip this, okay? Because the aluminum is actually turning into aluminum ions. Now, the electron flow goes like this. It always goes through the wire from anode to cathode. Okay, that's how electrons always flow through the wire. If we think about the salt bridge, and I don't have much drawn in here, but if you have inert ions in that salt bridge, well, your cations are going to be attracted toward the cathode, which I think kind of makes sense, and the anode, well, your anions are going to be attracted toward the anode through the salt bridge. I think that kind of makes sense as well. Okay. Now, as we think about this, let's write the overall balanced equation. We know that the cathode half reaction is written as it is, but the anode, think about like anti, that's the one that you flip. So that's why it's written as Al yields Al3 plus 3 electrons. And to balance this reaction, we have to multiply the first half reaction by 3, because you want those electrons to cancel out. And now, when you add this up, we can clean it up, and there is our balanced equation for this galvanic cell. Okay? And generally speaking, when you have metals like this, the cathode is going to increase in mass, so the silver is going to get more massive, the cat gets fat, and the anode, the aluminum here, is going to decrease in mass. So there we have our entire course in a relatively quick cram session. I hope you've been able to learn something from this video, from this cram session. If you have, please hit that thumbs up button if you've stayed with me this long. I really appreciate it. And I know you're all going to do great on your AP Chemistry exam. I have lots of review videos, the ones that are have each unit summarized in 10 minutes. I've got the longer videos for all 91 of the topics in AP Chemistry, so don't forget about those if you need more review. And if you haven't subscribed, go ahead and subscribe so that after the AP exam, you can come back and watch my problem walkthroughs for this year's AP questions. I'm going to try to get those online as soon as I can. And I wish you all the best for your AP exam. I hope you spread this video around to all of your friends and your colleagues and everyone in your AP Chemistry community. Thanks for watching, and I hope to see you very soon.